if you just note this sentence, follow every molecule in its course, that means you are collecting information. And what was shown, not during Maxwell's time, but later on, was that information can have or has entropy. The first person who realized that was a brilliant physicist by the name of Leo Szilard, who proposed that in 1929 in his PhD dissertation in Göttingen. He was a Hungarian physicist who then moved to the US and did many other things. But what his first important contribution was to that question of entropy. So what was argued was that, at least in principle, Maxwell's demon did not violate the second law, because while the entropy of the gas was going down, the entropy of information collected by the demon was going up. And so if you count both together, then there was no absolute reduction in entropy. So you're not violating the second law. But it was not clear if this could be done in practice. This was just theoretical. And I say that Leo Szilard proposed this in 1929, the idea of information entropy. The person who is really recognized for that is Claude Shannon, who's considered the father of information science, who really developed that much more fully in 1948 when he was at Bell Labs. And later on, other theorists contributed to this, Ralph Landauer and Charles Bennett. I've met both of them. Landauer passed away, but Bennett is still alive. They're both at IBM Research. And they explained also that there must be a step that's irreversible in this process. And the irreversibility in this case was the erasure of information. So if you store it, let's say on a computer, when you erase it, that makes it irreversible. Okay, so now the question is, can this be done? And maybe coming back to this picture, there's a saying in English, maybe you've heard it before, that says that a picture is worth 1,000 words. However, I would say that a bad picture takes many more words to correct. And I would argue that this is a very bad picture, but it's the picture that we all learn in school. And I'll explain to you why it's a bad picture in a moment. But if you believe this picture, if you take it very literally, then I would argue that Maxwell's demon is still impossible. Now, there have been claims of Maxwell's demon experiments in the past, just like people claim to have made Schrödinger cats, although, as I argued before, I don't think the Schrödinger cat has really been done, even though we've done toy experiments, not the real thing, because Schrödinger had something very different in mind. Likewise, with Maxwell's demon, people have done experiments with a single particle. And if you have a single particle in a box, you can watch it, whether it's a macroscopic particle or even a single atom. You can detect single atoms with fluorescence or using cavity QED. And so people have done what I would call demonstration experiments, and then claimed this is Maxwell's demon. And that's okay, these are demonstrations, but they're not, first of all, they're not useful in any way. And I don't think that they really are what Maxwell had in mind. Maxwell really was thinking about very large ensembles. Otherwise, it doesn't really make much sense. And so the real question is, can this be done? Or is it just a thought experiment? And you know, when you analyze these things, you're never sure with thought experiments, where's the flaw? For example, people wonder, well, could this wall, this trap door, maybe it has friction, and maybe you're losing energy from friction. Maybe that's a problem. And all kinds of questions you might ask. How would a demon do this? And it's clear, though, that if you have a very large number, like Avogadro's number, then the idea that you would follow every molecule in its course, I think even today, 150 years later, is still impossible, as far as I know. So that's why this is a very bad picture. And then the question, though, is Maxwell's demon real? And my message to you today is that, yes, it is real. We can do it exactly as Maxwell proposed. So in that sense, it's much farther ahead than Schrödinger's cat. And in addition, what I'll show you is that this is going to be really useful. In fact, as I'll show you tomorrow, this is going to save people's lives, surprisingly, because it has applications to medicine. So let me come back to a question that we asked some time ago in around 2004 in my group. We asked the following question: can we make a one-way wall for atoms? What does that mean, a one-way wall? Well, again, let me draw the canonical box. And let me have our particles here. A one-way wall would look like this. It would just be a wall where an atom can go this way, but this way is forbidden. Now, if we could construct such a one-way wall, what would happen? Well, eventually, the atoms that are here would all move over there, but the atoms that are here can't go this way. So if you just wait, everything will be on this side. That's the question. Can we make a one-way wall for atoms? And so we proposed this in a conceptual paper in 2004, but the paper was only published in 2005. And we showed that, yes, you could construct it in a realistic manner, and you could use that to cool atoms in a different way than laser cooling, a fundamentally different way, because it would not use the momentum of the photon as in laser cooling, but it would use the entropy of a photon. And I'll show how that works. So it's a different way of thinking about things. And this paper was published in PhysRev Letter in 2005, together with my former student, Artem Dudarev, and Nat Fish, who's a plasma theorist, Princeton, and Chen Yu, who's a condensed matter theorist. So this is an unusual collaboration. But we made a construction, and the key ingredients are, I would say there's two ingredients that you have to have. You have to have a conservative potential plus an irreversible process. If you just have a conservative potential, like a magnetic field, you can create a potential, but it's symmetric. In other words, you don't break the directionality. It can work the same way either way. So how does this work? And maybe before I explain how the one-way wall works, let me remind you of something known, and probably known to many of you, in atomic physics called optical pumping. This was invented by Alfred Kastler, who won the Nobel Prize in Physics for this work in 1966. So how does that work? Well, if we consider, let's consider, to be specific, an atom where we have a ground state with three, it's a J = 1 ground state. So we have three magnetic sublevels, M + 1, 0, and -1. And then we have an excited state, also J equals 1. Okay? Now, initially, especially if you imagine atoms being prepared by heating them in an oven to vaporize them, you will have atoms in a equal distribution, a statistical mixture of being equally likely in all three magnetic states. And by the way, the way an atom responds to a magnetic field depends very critically on which state you're in. So if you're in the +1 state, you are repelled by the magnetic field. In the 0 state, you're unaffected by the magnetic field. And in the -1 state, you're attracted. Now, Kastler's idea was that by using quantum selection rules with polarization of the light, if you tune a laser on resonance, let's imagine that you tune a laser so initially it's polarization, so it's on resonance between the two transitions, but let's imagine that it's sigma plus, circular light, circular polarized light. In this case, right circularly polarized light. Well, then the quantum selection rule is that delta M equals +1 on absorption. What that means is that if you're in the -1 state, you go up to the 0 state here. And if you're in the 0 state, you go to the +1 state. When you fall down, shown by spontaneous emission, you can fall down into any of these possible states. But notice that when you're in the +1 state, you can't absorb anymore because there's no +2 state up here. And so you accumulate after several cycles. If you absorb and re-emit several times, you will pump the atom into the +1 state, and then it becomes dark. In other words, it can no longer absorb light from the laser. That's we call that a dark state. Now, if you were to use linearly polarized light, you would have, in this case, in linearly polarized light, delta M equals 0, and you would go up, but you could decay like that. And eventually, and likewise go up and decay like that. But 0 to 0 is not allowed. So after you fall into this state, you're also stuck, and that's a dark state. So I can optically pump into the +1, the 0, or the -1 if I were to use left circularly polarized light just by choosing polarization. Now let's see how we can, and let me give you another example, because this was for a J1 to 1 transition. It's in the case of an alkali, which many of you are familiar with, for example, lithium-7. If you look at the ground state of lithium-7, in that case, you have two hyperfine states, F equals 1 and F equals 2. And then in weak magnetic field, as a function of B field, you get, in this case, you get 3 states. And in this case, you get 5 states. And that's the linear regime, the linear Zeeman shift. But in strong field, what you find is that these states go up, and this state goes down, and in strong field, this behaves like a J equals half. So this is like +1/2 and -1/2. So interestingly, for an alkali atom, if you just pump it into the lower hyperfine state, it's a -1/2, which we call, this state is called a high field seeker. And this is this one is a low field seeker. These are the states that we can put in a magnetic trap. That's for trapping and cooling, like for making Bose-Einstein condensates. But this is a simple picture. Now in a J equals in a 1/2 state, you have spin 1/2 and minus 1/2. In an external magnetic field, well, one shifts one way, the other shifts the other way. And if you have a gradient, then this one is going to be repelled by the magnetic field, and this will be attracted to the magnetic field. Okay, so that would be an example where in an alkali where we can do optical pumping into a very simple state. Now, in some cases, it's far from simple, and optical pumping is, perhaps you could say, is it a general property of atoms? In fact, what we showed in this paper with several authors, including myself and Dima Budker, efficient polarization of high angular momentum systems, and this was the publication. What we showed is that even when you have a large spin, and this could also be in a molecule, that you can do optical pumping, but optical pumping relies on a spontaneous emission process. That is what makes it irreversible. It's not the stimulated process, but it's the spontaneous process of decay. And what we showed in this paper is that the minimum number of spontaneous events that you must have is 1. But that actually is enough to make it irreversible. So even in a multi-spin, large spin system, you can optically pump efficiently into a particular magnetic state, and you only have to have one spontaneous decay in the end. The rest you can do with stimulated processes. But the rest of my talk will be about simple spin systems like spin 1/2, like alkalis. So we don't worry about it. Okay, let me come back to this one-way wall picture. And now I'm ready to explain how it works. So excuse me. Luckily, I don't have to wear a mask at home. Otherwise, that'd be a problem. Okay, so here's our chamber. And let's imagine now I'm going to have 2 colors. One color is red. So this is going to be a J equals 1 to J equals 1 transition. So we have, I'm going to denote red as M equals 0, and blue is M equals 1. So let's imagine that we start off all our atoms in the 0 state. And so in phase 1, we optically pump atoms to M equals 0. And that's why they're all red. All right, then in 2, turn on B field in center. And I'm going to write that here as a B field. What happens? Well, I can't ask you because I don't see the audience, but I think it should be clear that nothing happens because the atoms are in the M equals 0 state, so they don't see the magnetic field. They don't care. But now, let's turn on a laser, and let me make it a green laser. So this is a green, the green line is a laser beam that is tuned to optically pump every atom from the 0 state to the 1 state. So now what happens? Let's go back to this picture. Let's consider what happens to an atom on the left side. If this atom, and shown in red, goes this way, when it goes through this green laser, it's converted to an m equals 1 state, right? But an m equals 1 state, I'm sorry, my clock is chiming. An m equals 1 state is repelled by the magnetic field, so it turns around. What happens to an atom on this side? Well, let's look at this atom here. This red atom is m equals 0 state. It can go through, so it goes through the magnetic field because it doesn't see it. But then it goes through this beam here and comes out, it turns from red to blue because it's pumped into the m equals 1. Now, if it tries to come back, it's also turned around. So if we just wait now, with this configuration, this very special configuration of our B field and our laser beam, now if we just wait, all the atoms now are on this side and they're blue because they're converted to m equals 1 atoms and they can't come back. So what we've done is we've made this one-way wall. In principle, this works. Now, of course, you know, the question is, what about the experiment? And the experiment, which we did a few years later, proved that it works, not just in conceptually, but we proved experimentally that it works. And that was with my former student, Gabriel Price et al. From my group, PRL 100-093-003, 2008. And it works, the experiment works. We were able to compress phase space. So phase space density we increased in that paper 25 times, and later in a second paper, we did it 350 times. So this kind of cooling really worked. That's great. And I think it was surprising in one sense that we did not use we did not use the photon for its momentum. So this kind of cooling was not like laser cooling. In fact, it only relied on magnetic fields in general and optical pumping. So now the question you might ask is, what does this have to do with Maxwell's demon? Well, there's a saying also in English, if it walks like a duck and quacks like a duck, it's a duck. So this behaves just like Maxwell's demon, except there's no demon. Where's the demon? So maybe the question we can ask is, what would Maxwell say? And normally I couldn't, of course I can't ask him. just like I can't ask Schrödinger, but I can guess. And with Schrödinger, I would guess that he would say, no, you have not made a Schrödinger cat state. But Maxwell, I think he would say he agrees that this is exactly what he wanted. And the reason I say that with confidence is because of a letter that he wrote. And this letter, in which he says, this letter was written in 1870. I'll say in a moment to whom. He says, I do not see why even intelligence might not be dispensed with and the thing made self-acting, allowing all particles going in one direction while stopping all those going the other way. In other words, Maxwell was saying what you really need is a one-way wall. But he didn't know how to construct it. But his feeling was that this could be an automatic device. You don't need this intelligent creature. So he says intelligence can be dispensed with. You don't need intelligence. That's a crucial point because the need for the demon made it impossible. But if it's just a device that works, then as we've shown, it actually does work. And this was a letter that he wrote in 1870 to another friend of his, Lord Rayleigh. It's interesting, Maxwell himself never became a lord. I'm sure he would have, but he died very young. He was only 48. But he was friends with Lord Kelvin and Lord Rayleigh. So now, again, the next question that we have to ask is, what happens with the second law? Well, we have to explain where the entropy goes. And this was explained in a paper that I wrote with two colleagues, two theoreticians, Andreas in JPhys D39 3833 2006. But what we showed, actually, we did an analysis of the entropy. So where is the entropy going? So we think about this problem. We have imagine our atom is a three-level system. So this actually would not work in a two-level system. You need at least three levels, but more is okay. And in the case that I described, we identified this level with m equals 0, and then this one with m equals 1. And we excited with a laser to the upper state. They're both in this case ground, but let's think about them as three levels, even though these are just magnetic levels in the ground state. But it spontaneously decays back to this one and changes it irreversibly from 0 to 1. Now, where's the entropy going? So the entropy is the scattered photon. Why is that? Well, if you think, what is a laser beam? A laser beam is a source of very directional photons. Each photon is going in the same mode of the electromagnetic field. And you ask, what's the entropy of a laser? So we can say that a laser entropy is approximately 0. It's a very low entropy state. And Max is back, but not for long. So what happens though when an atom absorbs, here's the atom, when the atom absorbs this green photons, and then it emits them later in spontaneous emission in all directions. we haven't changed the frequency much, but we've now randomized the direction. Instead of coming out in one direction, it comes out in all directions, into 4 pi steradians. And that has increased the entropy of the photon field. And so in this little paper, we actually calculated this, and we showed that the entropy increase of the photons is compensating for the entropy decrease of the gas. So there's no mystery here. We understand that the demon is just a laser beam. The entropy is given away, and we assume that when a photon is spontaneously emitted, it doesn't come back. It's absorbed by the walls, or it never comes back. So it's lost. And that's like the erasure that Landauer required. So everything we've done fits in, except that this really works. And you don't need this intelligent creature. That's a crucially important point. And I think people before hadn't realized that. And that's why our experiment and our way of looking at it, I think, is the first realization of Maxwell's demon as Maxwell proposed in 1871, so about 140 years later. All right, so now you can say, okay, that's nice, but so what? Does it really, is this important? In other words, why should I care? Well, I'll give you an idea, but I suggest you read, you can read a review article that I wrote about general methods of cooling, an invited article in Science 324. This review article where I explain all about this cooling method, and also I talk about our magnetic stopping methods, which are separate, but I don't have time to talk about them today, but we've used pulsed magnetic fields to stop atoms. So for the organizers, how much time do I have? Since we started late, I don't remember. Can anyone hear me?
A little break, but it's okay now.
How much time do I have?
For 10 minutes.
10 minutes?
If you want, yes. Mm-hmm.
10 minutes, okay, perfect.
Thank you.
That's all I need.
Okay.
There's also a popular article in Scientific American from 2011, which was entitled Demons, Entropy, the Quest for that I wrote. So if you want just a popular, this is not written for experts, but since you're all students of physics, I would recommend you read this article. Okay, so in the time that remains, and this is taking me longer than I thought, but let me just say that there's no question that what we did is Maxwell's demon, and it works. And it does compress phase space, but it didn't conserve number, because essentially the picture that I drew was one-dimensional. And in reality, you have to do this in 3 dimensions. So we proposed a method in 2014 rather, which we called magneto-optical cooling, or MOP cooling, and that's the reference. And when I say MOP, it's like what you use to sweep the floor, because that's kind of how it works. You sweep atoms around, and the experiment still has not been done, and so we're hoping to collaborate with someone, perhaps in Sao Carlos, to actually do the experiment. But the basic idea is that if you imagine turning off, let's turn off the magnetic trap. So imagine we trap atoms magnetically and then turn them off, turn it off and find a cooling method that works fast. So let's imagine that we have a cloud, and just to be consistent with my previous notation, this is m equals 1, and we have m equals 0. So imagine we have a cloud. In this case, we will start the cloud because it's trapped magnetically. I'm just going to draw a few atoms. And they're all in the m equals 1 state. And there's a certain delta x. Here. Then let's do spatially resolved optical pumping so that half of the atoms on the right will be put into the 0 state, and the other half will remain in the 1 state. Then so this is optical pumping. Then let's do a magnetic kick. And during the magnetic kick, we will accelerate the atoms on the left. We'll first accelerate them and then decelerate them so that at the end of that magnetic kick cycle, we will have a smaller distribution in space, but the atoms will be mixed together. So there'll be blue. I'm sorry, I didn't use my right pen. It should be blue and red. And then finally, we do optical pumping, and we end up back to all being blue. But if you look at the beginning and the end, you see that now we've made delta x naught x naught over 2. So what we've done is we've folded the distribution fast. And so this kind of cooling in space is geometrically fast, 2 to the n, where n is the step, and it compresses phase space. Now you can do the same thing this was done in real space. You can also do it I could replace, instead of delta x naught, I could do delta p naught. And this, instead of delta x naught over 2, I would get delta p naught over 2. The way you would do it, instead of spatially resolved, you'd have to use stimulated Raman or Stirop, but I don't have time to go into the details, but it's equivalent. So you can either compress in real space or momentum space or both. And the answer is that you can have rapid of phase space. So this MOP cooling in principle is a general method. What importantly, no loss of atoms in principle, and it compresses phase space. So in principle can reach high but it can be fast. This whole thing can happen in milliseconds. So the experiment is needed, and I'll just close because I'm running out of time by saying that what are the applications of this kind of cooling, and why do we need it? Well, it's to get ultra large n in number of atoms. That has, up till now, of course, laser cooling trapping is extremely successful, but cooling, beyond laser cooling, you have to use, up till now, people have used evaporative cooling. And an evaporation is slow. It's not general. For example, it works on rubidium-87, but not rubidium-85 very well. And you throw away 99.9% of your atoms. So if you can do this fast in milliseconds or 10 milliseconds, and you throw away no atoms, this could allow to make extremely bright BECs, degenerate gases, Fermi gas. This would have implications for any kind of precision atomic measurements, such as atomic clocks or interferometers, where typically signal to noise scales like square root of n, but we predicted and we were funded by the Keck Foundation a few years ago to develop this into an ultra bright atom laser, where we predicted that you could get a flux of an atom laser that might be as much as 1,000,000 times higher than currently possible. And so this is not a small improvement. This could lead to big improvements in signal to noise. And this could be important for people have proposed atom interferometers for gravity wave detection. But they find that they need BECs that are much, much bigger. It could be used for a study of quantum turbulence, which I know is of a lot of interest at San Carlos in the Bagnato group. Other things like super radiant lasers. As the work of Thompson at Gila, where again, you get an n squared dependence. So it's even a more dramatic effect, because if we could get big increases in number, you could get enormous improvement in super radiance. So I'll close here. This is my talk, first talk today. Tomorrow, I will talk about how we use this to separate isotopes very efficiently, which have applications in medicine. It all comes back to this concept of Maxwell's demon and one-way walls. So thank you for your attention, and I'm open now for questions.
So questions, please come here. Come here, please.
Hi, Mark. Thanks for the great talk. If I get it right, this method of cooling can only be achieved with J = 1 to J = 1 transition?
No. That was just the example that I gave. In fact, it can be done with any case we've looked at, as long as it is magnetic. So it requires, at least for our magnetic kicks to work, we need a paramagnetic atom. But even alkaline earths can be optically pumped into a metastable state, or like calcium and strontium. And so it's not restrictive. In fact, it only requires paramagnetism and optical pumping. And as I showed from the paper with Dima Butker et al., we showed that optical pumping is extremely general. It can be done on large spin systems. So I think this is extremely general.
Thank you. More questions, please? Can come here. Pode ficar aqui em cima, que ele vai te ver.
Hello. So when you talked about how the photon gets scattered randomly, so you know where the entropy goes, right?
Mm-hmm.
Is that a way that I could see it, like from the information side of it? Like if the photon didn't scatter, like would I know about information about particles' positions or momentum? Like, can I see it the Landauer's principle way for where the entropy goes?
I'm not sure if I understand your question, but the photons are being scattered. We don't detect them, but we could detect them in principle. I mean, we could surround our chamber with photodetectors, and every time an atom crosses the one-way wall, we would get a click if we detect that photon. But As far as we understand, one doesn't have to actually detect them. The fact is the information is there.
Right.
It's just that it's given out, but it's not, we don't have, it's not,
If we
and one way to see that is our method is not a priori, like in the original Maxwell demon idea. That there, the demon had to see in advance to know what to do. In our case, it's a posteriori. It's after the fact. We could reconstruct it, but we don't have to. In fact, the device operates the same way. You don't have to think about this in terms of information entropy. You can just think about this as this is the way the one-way wall works. I like this explanation because it explains to me and to other people why the second law is not violated.
Yeah. We could recover that, and that is enough to know that entropy is there. I mean, it's a scattered light, so entropy is there, like thermodynamically speaking.
Thermodynamically, we are not violating the second law because we've increased the entropy of the laser of the photons.
Thank you.
More questions? In the chat? Also in the chat, we don't have questions, so we'd like to thank you a lot for your lecture. It was very nice. I like it so much for the way you did. And thank you, and see you tomorrow.
Okay. I'm glad it went well, even though there were some delays, but I'm glad you enjoyed it. Thank you, and I'll see you all again tomorrow.
Okay, see you. Bye-bye.
Okay. Bye-bye.